In this video, we will learn to design this pavilion geometry, and set up a parametric definition to make several iterations of this form. Before we start building the definition, let's cover the steps and goals required to design something like this. We start with a cylindrical mesh with varying radius at the top and bottom. Isolate the list of naked points. Anchor the points on the top, and few points on the bottom. Points on the bottom are split into two lists of anchor and non-anchor points. The non-anchor points are displaced using multiple load goals to create the entrance archway, while the bottom anchor points are anchored onto an arc, in the opposite direction to arrive at the final form. Remaining mesh is relaxed between these fixed boundary conditions. Let's begin with the definition. You may open the Grasshopper file provided in the resource folder to follow along. Set the drawing units to centimeters. The first step is to model the cylindrical mesh. Draw two circles, one at the default XY plane with radius 150. And the second circle at 400 units above the default plane, with radius 60 units. Divide both circles into 48 segments using the divide curve component. Note that we are using the number 48 here because it's a multiple of 3. We will be bifurcating the bottom points into 3 lists, out of which some points will be anchored, and some will create the entrance archway. If the objective is to create 4 archways, then the division count should ideally be a multiple of 4. Join these points using the polyline component, with the closed parameter set to true. Explode these two polylines to get 2 lists of line segments, with 48 lines in each. The vertices output gives the list of naked points to be used for anchor and load goals. Merge the two lists to pair the respective indices from both lists into separate branches. This is done by grafting, and simplifying the inputs of the merge component. Now both input data trees have identical paths. The output from merge component is a list with 48 branches, with 2 items lines in each. Connect the output from merge into the loft component to generate 48 lofted strip surfaces. Use ISO trim, and divide domain square, to subdivide each strip into 10 smaller surfaces each. Join all these surfaces into a single B-reps, using the Join B-reps component. Flatten all B-reps input of Join B-reps function. The resulting B-reps must be converted into mesh, using simple mesh component, to retain the B-reps topology in mesh geometry. Output from simple mesh is the base mesh to be used for simulation. Connect the mesh to show and edge length goals. Set the length factor to 0.1. Next, we need to assign the anchor goals. Find the two sets of points, identifies during explode step. These points are derived by exploding a closed polyline curve, and the first and last point on this list is duplicate. Remove the first point in both lists using the cull index function. Both lists should have 48 points. Out of the two sets of points, the points from top curve are anchored in position. Use an anchor goal to set up the top anchor. For the bottom points, we will start by partitioning the list into 3 branches of equal sizes. Use the partition function, and set the size parameter to 16. Better yet, use the list length function, to get the no of points in the list, and then divide by 3. We use the number 3 as denominator, because it is the number of archways intended. Connect the result to the size input of the partition list function. This returns a data tree consisting of 3 branches, with 16 points in each. Use PointList to visualize the order of these bottom points. Let's choose the first 6 points to anchor for each branch, and the remaining 10 points for the archway. Use list item to extract index 0 to 6 from the partition list output. This step extracts the first 7 points from each branch of the partition list output. Connect these points into a point container component, and tag them as anchor points. This data tree should have 3 branches with 7 points in each. Extract the remaining points by connecting the partition list output to cull index component, and cull index 0 to 6. This returns a data tree with 3 branches, and 9 points in each. Connect these points into a point container component, and tag them as load points. For load simulation, 2 separate load goals will be used to create the archway. The first one will translate the point in Z direction, and the other will move it away from the center, or the origin in this case. Set up the first load goal with the Z vector as force vector. Connect a numeric slider to the unit Z vector to change its magnitude. Set up the second load goal by generating 2 point vectors between the origin and the load points, and using them as force vectors. Before connecting to the force vector, unitize the input vector, and use a numeric slider to set the magnitude of this vector, using the amplitude function. This will help in controlling the mesh output by changing the slider. To visualize this vector, use vector display function. The arrow must be pointing away from the center. The last step in this process is to assign target points for the anchor goal. As an aesthetic decision, we will try to reverse the curvature of bottom anchor points. This will improve the continuity of form, and the way it meets the ground. It will also present methods of manipulating edges as per design objective. Base anchor points are divided into 3 branches. Let's use point list to visualize their indices. Isolate the first and last point on each branch using the list item, and draw a line between them. Find the midpoint of each line, and draw a circle of radius 50 units. We need to divide the circle into 2 arcs, and use the inner arc as the target curve for our anchor points. Before dividing the circle, let's move it slightly away from the origin to reduce the size of the inner arc. Create a vector 2 point between the global origin and the midpoint. Unitize the vector. And set its magnitude to 10 units using the amplitude function. Use this vector to move each circle away from the origin. To divide this curve, we use these line segments and the intersect curve command. Connect the circles to input curve A, and the lines to input curve B. This gives us parameters that can be used to shatter the circular curves. Shatter the circles using params A, and we get 2 curve segments for each circle. To identify which of these curve segments is the inner curve, we can check their length, and the curve with the shortest length would be the inner curve. Connect the shattered curve to length component. And connect the length output to sort component. Also, connect the curve segments to values A input of the sort component. The resulting list is sorted as per ascending order of curve length, which means that the first curve in each branch is the target curve. Use list item to isolate the target curve. Now that we have a list of target curves, and a list of base anchor points, we need to identify the target points for each anchor point. Firstly, let's align the direction of target curve with the order of bottom anchor point list. To do this, we will isolate the endpoints of the target curve, and check their distance from the first point of each branch of anchor points. If the target curve is aligned with the point list, the distance from start points will be lesser than the distance from endpoint. Use smaller than operator to test this logic. Resultant Boolean list will be used to dispatch the target curves between aligned and non-aligned curves. List B consists of the non-aligned curves, which must be flipped using flip curve. In this case, all target curves are non-aligned. Output from flip curve function is the list of aligned target curves. Next, Divide each target curve into 6 segments. You may use the list length component to extract the number of points in each branch. Then use expression x-1 to get the division count. The resulting points list consists of 3 branches, with 7 points in each branch. Draw lines between anchor and target point to verify the position and index target points list. If everything is in order, connect these point lists to the anchor goal. Merge all goals, and connect with Bouncy Solver. Reset, and enable the solver. Use list item to isolate the first item from the output list, which should be the simulated mesh. The output mesh does not look the way we intended it to be. We must tweak the load goals to improve the proportions. Set the Z load goal to 28 units, and the other load goal to 50 units. Now it is closer to the shape we set out to achieve. As an additional goal, we may add the pressure force to expand the mesh uniformly. Connect the base mesh to the pressure goal. And set the strength to 0.01 units. Reset the solver, and we see that the mesh geometry expands a bit. And there we have it, a mesh geometry designed as a pavilion. This mesh can be further transformed using various mesh-based modifiers. Weaverbird's transform modifiers have multiple options like picture frame, mesh thicken, mesh offset, stellate, etc., to add relevant details as per your design. The reference Grasshopper file has multiple options for quick detailing of the model. Apart from quick transformation modifiers, there are numerous ways to fabricate the form as well. It can be discretized into strips, or use stereotomy to develop optimized and custom brick modules to put it together. Or use the mesh vertices and edges to create a metal structure out of it. We will explore the strip-based fabrication strategy in Module 04 of this course. As a practice exercise, try to build this grasshopper definition from scratch, and then vary the parameters to create variable results. For example, to change the number of archways to 4, find the mathematical operator that controls the initial partition of base points, and change the denominator to 4. Try varying the initial surface division, or the force vector, or the anchor points and document the results. The next chapter will cover how to simulate a network of joined vaulted structure.